Okay, in this video we're going to be looking at some examples from Chapter 17 out of Hibbler, and that chapter is the kinetics of planar rigid bodies. And so first one will, and of course that brings in the idea of rotation when we talk about rigid bodies. What we're going to be looking at first is a couple of problems where there actually is no rotation, but there's the possibility of rotation, what I call is the problems where they're fixing to rotate. Or if we're talking about automobiles or bicycles, it'd be problems where they're fixing to pop a wheelie. So we have, as the problem says, a pickup truck, and I keep grabbing the mouse to point to things, but you can't see that, so I'm going to point with my pen. The pickup truck weighs 3220 pounds, reaches a speed of 30 miles per hour from rest and a distance of 200 feet up to 10% incline with constant acceleration. Calculate the normal force under each pair of wheels and the friction force under the rear driving wheels. The effective coefficient of friction between the tires and the road is known to be at least 0.8. This might be a good kind of problem to revive the transition equation ideas or the state equation ideas. And what we have is two states: a state 0 where the pickup truck is at rest, and we have a state 1 where the pickup truck is at 30 miles per hour, and there has been a delta x of 200 to get us from here to there. That's probably an acceptable way to show that. So delta x of 200 feet, 10% incline, and we were told constant acceleration. So we'll transition with a equals constant. And of course we will have to find that, let's see, acceleration. So this is the transition part of the problem, and then what we want to know is some of the forces. So let's deal with the problem. First of all, the transition piece says we're going to travel 200 feet and have a change in velocity under constant acceleration. So we can go to the near the upper left hand corner of our equation sheet and get our equation that says our final velocity squared is equal to our initial velocity squared, which is 0, plus 2 times the acceleration times the distance we travel. Or this thing says that our acceleration is going to equal velocity squared over 2 times the distance traveled. We'll convert our velocity, 30 miles per hour, into feet per second. Square it, divide by 2, and the distance traveled, 200 feet. Or we come up with an acceleration of the center of gravity of the truck is 4.84 feet per second squared. Okay, now we have a slope that was said to be a 1 in 10 slope, so we'll take the inverse tangent of 1/10, and we'll come up with a slope angle of 5.71 degrees. And now what we want to do is take a close look at the free body diagram of this truck and see what we have on it. We have a rear wheel drive truck with a friction force that is propelling the truck up the hill and allowing it to accelerate. And we have a normal force under the rear wheels. We have normal force under the front wheels, but we do not have any friction force because it's not a front wheel drive or it's not a four-wheel drive. We also have the center of gravity given, and we have gravity acting straight down, but where our coordinate system is not in the gravity aligned direction. So we have a gravity component in the normal direction, W cosine of theta, and a gravity component in the tangent direction, W sine of theta, acting back down the hill. And notice X and Y coordinates are labeled. Those would be our positive directions, which makes that a totally good free body diagram. What we're going to do is sum forces in the X, sum forces in the Y, and then some moments about somewhere. We'll see that in just a moment, and we will learn what we can about the problem to come up with the forces. So first of all, sum of forces in the X direction equal mass times the acceleration of the center of gravity in the X direction. And the forces acting in the X direction would be friction, positive, this W sine of theta component of gravity, negative, and so we have friction component positive, gravity component negative. Let's go ahead and put an X on that thing. The mass of the body times the acceleration of the center of gravity in the X direction. And what we have here is one equation, one unknown, because we know the weight, we know the angle. We have already solved for the acceleration. That was the 4.84. So the only thing unknown here is the friction force of 804 pounds. We've learned what we can using sum of forces in the X. Now we'll go back to the free body diagram and sum forces in the Y. And what we're going to have for sum of forces in the Y will be gravity and the N1 force and the N2 force. And let's see, let me remember. Yes, calculate the normal force under each pair of wheels and the friction force. So this is not an impending rotate. We're assuming that we're not going to pop a wheelie. And so we don't know the normal forces. If we were about to pop a wheelie, we would set that front wheel force equal to 0. So in the Y direction, we have the, let me move this up a touch. In the Y direction, we have the normal force under wheel 1 positive, normal force under wheel 2 positive. We have the gravity force is negative, is equal to the mass times the acceleration of the center of gravity in the Y direction, but that is 0. Therefore, it is equal to 0. And so what we have is normal force 1 plus normal force 2 is equal to the normal component of gravity, W cosine of 30, which came out to be 3,200 pounds. That is one equation, two unknowns. And now we'll turn to our final equation. Sum of moments about the center of gravity is what we'll choose here, is equal to IG alpha. But in this case, the truck is not going to rotate, so sum of moments will be equal to 0 because the alpha is equal to 0. And our sum of moments about the center of gravity, let's look at this thing. We will have distances of 60 here and a distance of 60 there, and so we'll have N1 times 60, then minus N2 times 60. We're going to have to talk about that. Plus 24F. Let's talk about that. We have X and Y this way. We're going to say a positive moment. That wasn't labeled, so maybe it wasn't quite as good a free body as I thought at first. We have a positive moment this way, and so N1 times 60, horizontal distance to the center of gravity, will be a positive moment. N2 times 60 would produce a moment the other way. That would be a negative component. And our friction force, with a height of 24 inches off the ground for the center of gravity, friction times the center of gravity distance, would also be a positive moment. So we have positive, positive, only the rear wheel produces a negative moment, and that's equal to I alpha, but alpha is 0, which means we didn't even bother to compute I. Now, from our sum of forces in the Y direction equation, let's bring this down. One equation, two unknowns. Our sum of moment equation is another equation, two unknowns. That's a solvable pair of equations, and we get the normal force under the front wheel of 1440. The normal force under the rear wheels is 1760. But there is one nagging question remaining: is do the tires have sufficient coefficient of friction to produce the friction force that was needed to produce this acceleration? So we need to test that and see if this problem is possible. And so if you recall, our friction force was 804 pounds, and our coefficient of friction is no more than 0.8. And so 804 pounds divided by the rear wheel normal force would give us a coefficient of friction required to accelerate of 0.46, which is less than the 0.08 which is available, and so this problem hangs together and makes sense. Next problem is a problem where we are fixing to tip. So let's see, let me zoom in a little bit at first, then I'll have to zoom back out, but let you read the problem as well as possible. So we have a 2-pound bottle that rests on the checkout conveyor at a grocery store. The coefficient of static friction is μs equals 0.2. Determine the largest acceleration the conveyor can have without causing the bottle to slip or tip. the center of gravity is at G, which is located in the picture as being 8 inches above the bottom of the bottle, and we have a 1.5 inch. You know, that's kind of hard to tell. I think that's the distance from the center of the bottle out to the edges. We'll be able to tell that a little bit later. And so when we want to find the acceleration, that brings us to impending slip or impending tip. Now, here's the deal. We don't know which is most likely to happen first. The bottle might slip before it ever tips, therefore it never does tip. The bottle might tip before it slips, and therefore never reaches slip. We don't know which is true. This is one of those cases where we're just going to make a guess, and then we're going to see if our guess is plausible. And so what we're going to guess in this case is we're going to guess that this bottle is fixing to tip first before it slips. And here's where we're going to place that assumption. We're going to presume that because we're just about to tip, we might have viewed this bottle as having a normal force at the back end and a normal force at the front end. But now we're saying the normal force is alone at the back end, and there is no normal force at the front end because we are just about to tip over and rotate toward the left. So there's no normal force left on the front end. That's how we'll approach the problem. Here is our free body diagram. We have gravity acting downward at the center of gravity. We do have a friction force that the conveyor belt would impose on the bottle to accelerate it, and we have our normal force that is moved all the way to the back of the box, or back of the bottle. And so first thing we'll do is sum our forces in the x direction and set it equal to the mass times the acceleration of the center of gravity in the x direction. And our force in the x direction is only the friction force, and so we'll say friction force positive is equal to mass times the acceleration of the center of gravity in the x. Then we will sum forces in the y and say that sum of forces in the y is equal to mass times acceleration in the y, which is 0, because we are not traveling in the y and we have not rotated. We're not going to let it rotate, so we haven't accelerated in the y. And so our normal force, our forces in the y direction would include the normal force and the gravity force. So normal force positive, gravity force negative equals 0, and that tells us that the normal force is equal to 2 pounds. And then finally, since we're now in Chapter 17, we have a third equation available to us, and we will sum moments about the center of gravity. We'll use the moment of inertia about the center of gravity times alpha, but in this case we're not going to allow it to tip. We're just going to come close, so alpha is equal to 0. And so looking at our free body diagram, we have a friction force producing a moment about the center of gravity, and we have the normal force producing a moment about the center of gravity, and the friction force moment arm is 8 inches, so we use 8 over 12 feet. The normal, and that's going to produce a positive moment for the friction force. The normal force is going to produce a negative moment, and it has a moment arm of 1.5 inches, dividing both the 8 and the 1.5 by 12 to convert to feet. And we say the friction moment minus the normal force moment is equal to 0. And this is one equation and one unknown, because now we know the normal force. And so we can solve for the friction force, and that gives us a friction force of 0.375 pounds. And let's see, where are we going with this? We still did not know the acceleration, but now that we know the friction force, we're going to come back and get the acceleration. Pop to the next page. So yes, popping the friction force into the acceleration equation, as I just pointed out, will give us an acceleration of 6.04 feet per second. Okay, now an alternative solution to the entire problem is to use the alternative form of the moment equation. Sum of moments about a center is equal to IG alpha plus rho cross MA. And let me see if we have the equation sheet. Yes, we do. And so on the equation sheet we could use this form of the equation. Let's take a peek at the details of this equation. So sum of moments, and where is point O? point O can be any point we want, but it's going to be this corner. And the reason to sum moments about that corner is it is very convenient because both the normal force and the friction force produce no moment about that corner. So sum of moments about that corner is merely the gravity force acting downward creating a positive moment about that point O through a moment arm of 1.5 inches. So we have 2 pounds acting at a distance of 1.5 inches over 12 to give us feet is equal to our moment of inertia times the alpha of the bottle, but the alpha is 0. We haven't actually rotated, we're just impending rotate, plus, and one way to read this is the moment of the mass times acceleration vector about point O. So there is a mass times acceleration vector ma sub g. That mass times acceleration vector produces a moment about point O, which is a rho, let's see, rho like that, vector crossed with mass times acceleration vector. But the easier way to get that moment is to simply say it is the mass times acceleration times the perpendicular distance, which is the 8 inches. And so we have mass, we have acceleration, we have the moment arm of 8 over 12, and the only unknown in this equation is the 6.04 is the acceleration, and we get 6.04 feet per second out of that one in one step. And that happened so nicely because we didn't want the normal force or the friction force, although we have good reason to want the friction force and the normal force, because one of the questions we ought to come back and ask ourselves is, we made the assumption that we were going to tip before we slip, but tipping or about to tip, impending tip, requires friction force of 0.375 with a normal force of 2. So our mu is going to equal to our friction force divided by the normal force, and that was the 0.375 divided by 2, and 0.375 divided by 2 is just a little bit less than the 0.2 that we said would bring us right up to slip. So the friction required to make it tip is less than the friction required to make it slip. Therefore, it did not slip. Another kind of problem. Let me zoom in a little bit. Okay, we have a wheel that is going to be rolling down an incline of angle theta, and we have a mu static available, and the problem statement says, for the given coefficient of static friction mu s, determine the maximum angle theta which will permit the solid circular disc to roll down the incline without slipping. And so we don't have numbers for any of this. We're going to work it out using symbols and algebra. So let's zoom back out. Let's take a look at our free body diagram. Our coordinate system is slope aligned, not gravity aligned. Notice the direction of positive x, positive y. We have our gravity acting downward, we have a friction force acting in the upward direction, and we have our normal force. And we're going to write forces, sum of forces in the x, sum of forces in the y, and sum of moments equal I alpha. And we'll have to decide where we're going to write our moment equation. And one reason that we might want to write the moment equation about this contact point, and this is a without slipping kind of problem. So one reason to write the sum of moments about the contact point would be that the normal force and the friction force produce no moments about the contact point. So we don't have to worry about finding those. And so let's go ahead and find the moment of inertia about the contact point. And the moment of inertia about the contact point will be the moment of inertia of a disk about its own center of gravity plus the mass of the disk times the radius squared. And if we go to the back of our textbook and find the table of mass moments of inertia, we'll see that the moment of inertia of a disk about its own center of gravity is 1/2 mr squared. And then for the parallel axis theorem, to move it through a distance of r from G to C, then we'll multiply by an additional mr squared. So we go from 1/2 mr squared to 3/2 mr squared for the moment of inertia about C. Now we can say that the sum of moments about point C is the moment of inertia about point C times the angular acceleration of the disk. Sum of moments equal I alpha. Why don't we have, since this is not a permanent pin joint, why don't we have to add in another term? And again, let me go back to the notes earlier, because the version that we're using here is sum of moments about any point we like, is the moment of inertia about any point that we like times its alpha, plus a rho cross m times the acceleration of this point where we're summing moments. Okay, and so a question would be, for a wheel that's rolling, let's just talk about it right here for a moment. For a wheel that's rolling without slipping, and it could be on an incline or not, it really doesn't matter, and here is the point P that we're talking about in this equation. Okay, we need to talk about the acceleration of point P. Because this wheel is touching ground and moving without slipping, wherever the wheel and ground touch, they must share the same tangential acceleration. That acceleration would be along this direction, the tangent part of the acceleration. And the tangent and the acceleration of the ground in that tangent direction is equal to 0, and the wheel moves without slipping, therefore the acceleration of that point on the wheel in the tangent direction must also be 0. So that part of the acceleration is 0, but is there any other acceleration left so that we put it right here and maybe we have a cross product to deal with? And the answer is yes. We do have a normal direction acceleration because the wheel's rotating. But this rho cross MA, here's the center of gravity, and here is the rho vector, and here is the A sub n vector. They both point in the same direction. When we have two vectors that point in the same direction, the cross product goes to 0. So for a wheel rolling without slipping on a surface, it's not that the acceleration entirely goes to 0, but the cross product happens to go to 0. So for an instant center, which is a wheel, perfect circles only, we can say the sum of moments about the contact point on the ground is equal to I of the contact point times alpha. And that would be the instant center of the wheel as well. That's not true of all instant centers, but it's true of that instant center. So we'll say sum of moments about the instant center is equal to I about the instant center times alpha, and we've computed the I about the instant center. And things causing moments about that instant center will only be the gravity piece, and it would be the gravity piece in the x direction, mg sine of theta, times the moment arm of r. So here's the moment. I is 3/2 mr squared times alpha, which means since we're not working with numbers, we're just working with algebra, we can solve for alpha is 2g over 3r times the sine of theta. Now, what we want to do is, let's see, find the maximum angle theta that will permit it to roll without slipping. So we're going to assume that we'll continue to not slip. So we've got a piece of what we can get so far. We've got the alpha. Now we can say that the sum of forces in the x is equal to mass times the acceleration in the x, and our x portion of the gravity force would be mg sine of theta, positive, then minus the friction force equals mass times the acceleration of the center of gravity down the incline, and so that would be our sum of forces in the x. And then we have our no-slip condition in chapters 17, 18, 19, and 16. When we roll without slipping, we can say that the acceleration of a wheel is equal to r alpha. That's going to be just, and we're going to call that a kinematic equation. A kinematic equation. A equal r alpha, V equal r omega would be a kinematic equation. The change in angle is equal, the perimeter rolled is equal to r times delta theta, a kinematic equation. Now, taking these three equations, which involve acceleration and alpha, we're going to be and friction. We're going to be able to solve for friction first of all. Let's see, where did friction come in? Friction was one of the unknowns to be dealt with here, and acceleration brought in here. So we have, eliminating the acceleration and alpha, we have friction is equal to 1/3 mg sine of theta. Okay. Finally, we do need some forces in the y direction to bring in the normal force. So sum of forces in the y direction is equal to the normal minus the component of gravity is equal to mass times acceleration in the y direction, which is 0. And so we get the normal force is mg times the cosine of theta, and we have the friction force from earlier is 1/3 mg sine of theta. And now we can finally say something about coefficient of friction by relating the friction and the normal. Okay, we're going to continue to be able to roll without slipping if mu static is related to F over N, and plugging in the F that we got from the previous page, the N that we got from right here, we get that mu static is 1/3 the tangent of theta, and so that mu static is precisely F over N. It's not less than or equal, it's precisely that in this case, which is impending slip. And what we get is that the angle, if the angle is less than or equal to the inverse tangent of 3 mu, okay, because we inverted this equation. If the angle is less than or equal to the inverse tangent of 3 times mu, then our wheel will roll down the hill without slipping. If the angle goes any higher than that, then we will exceed the static coefficient of friction and we will slip. An alternative solution would have been to some moments about the center of gravity of the wheel rather than the instant center for the wheel, and that would only have brought in one more force to the moment equation, because the friction will have a moment about the center of gravity. The normal force still does not produce a moment about the center of gravity, but we won't use our moment of inertia IC, we'll use our moment of inertia IG, which is equal to 1/2 mr squared. And so we would say sum of moments about the center of gravity. Oh, let's see, let's go back to the free body. It does one other thing. It eliminates the moment about the center of gravity that comes from the weight itself. So the only thing producing a moment about the center of gravity is the friction force. And so the friction force times the radius of the wheel would be the moment about the center of gravity is 1/2 mr squared alpha, and the 1/2 mr squared is IG alpha. So this equation relates friction and alpha. We still have to use the two other equations that we developed to come up with exactly the same answer. Takes care of that problem. Of course we're going to have pulley problems in Chapter 17. So let's zoom in quite a bit and talk about it. If I forget to zoom out in this video, please remind me. Alright, so we have a wheel which has both mass and rotational inertia. We have a mass hanging from a pulley, and these two pulleys here and here are massless and frictionless. We could give them mass and we could give them moment of inertia, and that would be solvable, but it would definitely complicate the problem quite a bit. We'd have multiple masses to deal with. So we have enough problem to work with where the block has mass and now this wheel has mass for us to work with. Let's look at the problem statement. It says the 20 kilogram disc A, and I've been pointing with the mouse again. Sorry about that. It's just tempting to do. Let me now point with my pen. And let me go back and say, earlier when I was talking about pulleys being massless, that pulley and that pulley are massless. and inertialess, and this wheel has mass and inertia, and that block has mass. And so now 20 kilogram disc A is attached to the 10 kilogram block B using the cable and pulley system shown. If the disc rolls without slipping, determine its angular acceleration and the acceleration of the block when they are released. Also, what is the tension in the cable? Neglect the mass of those smaller pulleys. Okay, and what we're going to want to do is listen very carefully and see if Obi-Wan is speaking. And I believe in Chapter 17, when we face rope and pulley problems, Obi-Wan is going to speak and say, cut the rope. Let's move out a little bit. For those of you who are not in my class this semester, it's just a little inside stupidity where Obi-Wan says, cut the rope. And so we have the wheel, free body diagram, being pulled by the rope, presuming that the tension in the rope at the point where it's being pulled by the wheel is T. And then we have the block being supported by a pulley with 2 ropes, therefore the block is being supported by 2T, and the block is being loaded with its own weight. And we have defined down as positive, and we are defining to the left as positive in spite of what these coordinate systems show. And so we're going to need to work the Pulley equations, and we're going to need to write our sum of forces, sum of moments type equation. And so the Pulley equation could be written to say that the length of the rope going to the wheel plus 2 times the length of the rope going to the block is a constant. And so that kinematics would say 2 times the length going to the block plus the length going to the wheel is equal to a constant. And therefore we can say 2 times the acceleration of the block is equal to minus the acceleration of the wheel, where in this coordinate system down is positive and left is positive for that particular equation to be true. Okay, so now let's proceed on, and what we're going to do is write the equation that we can write here, which would be probably sum of forces and sum of moments, or maybe just sum of moments. We'll see what's useful, and certainly sum of forces here, noting the rope tensions acting. So for the disc, summing moments about the instant center of the disc. Okay, and the author likes to write, and so this is something I haven't talked about with you yet. The author likes to say sum of moments about any point P. So sum of moments about any arbitrary point P is equal to the sum of all the kinetic moments, and he uses sort of a squiggly m sub k about that same point P. Now, what are these kinetic moments? These kinetic moments are I alpha plus rho cross m times the acceleration, rho cross ma. Okay, and so we'll see how the author puts that together. And so our sum of moments about the instant center being point P is equal sum of those kinetic moments about that same instant center point P. And since point P is down here, the only moments that we'll have acting about that will in fact be the rope tension. And he has declared acceleration to the left as positive, but alpha in this direction is positive. And so did we put T in? No, it looks like we're going to have an overall moment as plus if T is going to cause a moment about this point as being positive. We're going to have to see how the author works out his coordinate system. We're going to have to be very careful. Okay, so the author says yes, our rope tension acting about the wheel times the radius of the wheel of 0.2 meters is the only moment acting on the wheel. And then we have two terms, which would be that kinetic moment, and it is 1/2 m r squared alpha. And what that is Ig alpha, and then mass times r squared times alpha. What is that mass times r squared alpha? Okay, first of all, let's talk about this one. Mass times acceleration, ma. Now the moment, so our kinetic moments is the I alpha plus the moment of mass times acceleration about our point P. And so this the moment would be mass times acceleration times r. That would be the moment arm. But the acceleration itself is equal to r alpha. So the moment of ma acting through, or the acceleration ma acting through a distance r, where a is equal to r times alpha, is ma times r, and a is r alpha. That's m r squared alpha. Probably didn't say that beautifully. M r squared alpha. Okay, now this m r squared alpha is m, let's see, r alpha. That's ma. Then times another r gives us the m r squared alpha term. Is one way of looking at it. Or on our equation sheet, sort of getting low in my stack, but let me find my equation sheet. We also could have solved it, or we could have said the sum of moments about point P is I alpha, Ig alpha, plus rho cross ma. We're simply using this equation. Two ways to view it. Let's see. Let me say one other thing about this. What if we have multiple objects? It is possible to write this equation for one object, and then if we wish, we could write this equation for a separate object, and then if we wish, we could add those two equations. If each equation is true and we add them together, then that's still true. So if we had multiple objects here, each causing moments about some point P, and each having kinematic moments about that point P, this could be the sum of moments about a system of objects. This could be the kinematic moments of a system of objects, and the equation would still be true. Okay? And so, and I think we're going to do that in just a minute. Let's get back to where we were. Okay, so sum of moments is equal to the sum of the kinematic moments, or sum of moments about the instant center is Ig alpha plus rho cross ma. Either way, we get that term. Then for the, and that's all we're saying for the disk, because it brings in the alpha and it brings in the tension force. That's what we really need. Now for the blocks, sum of forces in the y direction equal mass times acceleration of the center of gravity in the y. And oops, you can't see that, sorry. So for the block, sum of forces in the y direction equal mass times acceleration of the center of gravity in the y direction, and the mass is the the weight is mass times acceleration of gravity minus two tension forces, gravity acting down, two tension forces acting upward, let's see, is equal to the mass times the acceleration of the block. So we have an equation that involves tension and acceleration, tension and acceleration, acceleration showing up for the first time, but in this one we had tension and alpha both showing up for the first time. So we have two equations and we have three unknowns, but now we have an equation which from kinematics, let's see, an equation from kinematics which relates the acceleration of B and the acceleration of A, but we don't really want to talk about the acceleration of A. So this is an equation. Let's go ahead and follow it through this way. Let's call it this way. So now we have another equation which brings in the acceleration of B, but we already had that. We have the acceleration of B right there, but it brings in the acceleration of A. We haven't encountered that before. So now we have 1, 2, 3 equations, but we have 4 unknowns. Okay, but we also can say that the acceleration of the center of the wheel is the wheel radius times r alpha. That's a kinematic equation. A is equal to r times alpha. This is now our 4th equation, bringing in acceleration and alpha, no new unknowns. Okay, and so we can solve all of these equations for these unknowns, and we come up with the acceleration of A as 0.755. We get that alpha is equal to, this is the acceleration of B. We get that alpha is equal to 7.55 radians per second squared, and we get a tension of 45.3 newtons. Okay, a lot of pieces to this thing. Let me just zoom out to be sort of look at the big picture on the thing. What did we do? We sum moments on the disk. Sum moments on the disk using the free body for the disk. We sum forces on the block using the free body for the block. We used the rope equations to write a kinematic equation that comes purely from the ropes. And then we wrote a rope equation that said the acceleration of the center of this disk is equal to the radius of the disk times alpha. That's a kinematic equation, and so A is equal to R alpha is true if we have no slip. Now, what if it were slipping? Then this kinematic equation is no longer true. That'd be a false statement if we're slipping. But if we're slipping, we'd know something else. We would know that friction is precisely mu times n. So if we're slipping, we know that truth. Sorry, if we're slipping, we know F equals mu n, and it's a mu k times n. If we're slipping, we know that truth. If we are not slipping, we know that truth. So one way or another, we're going to know a final equation that's going to help get the job done. Now, it was my thought that the author solved this one 2 different ways, but no, I guess he didn't. Okay, this is your homework problem. Yeah, I thought the author did solve that other one 2 different ways, but I don't have it in print. I might take just a moment and see if I can find that before I sign off on the movie. This is your homework problem, and I want to talk about one little piece of the solution, which is, and I want to talk about 2 options for solving this problem. So let me zoom in. And what we have is a composite object made up of 2 very simple objects. Now, the simple object is, one of them is a disk, okay, and that's a sphere, so we'd have to get the right mass moment of inertia for a sphere. We have a sphere whose center of gravity is right there, and then we have a rod whose center of gravity is right there. The sphere has a mass. The sphere has a mass moment of inertia. The rod itself has a mass, and the rod has a mass moment of inertia, and each one has its own centroid. And so, and this is something the author likes to do. You'll see him do in some examples. He's going to say the sum of moments of this entire object. Now let me zoom out a little bit. Try to keep the picture and the equations on the page. The sum of moments of the entire object about an interesting point is equal to the sum of all the kinematic moments of all of the objects that are in the system. Now, the point that we're going to use to sum moments is going to be point O right here, which is a pin joint, okay, or an instant center for the system. And the key reason we're going to sum moments on the body about that point is there are some forces passing through that point because of the pin, and we don't know what those forces are, but we'll eliminate those forces from the moment equation by summing moments about point O. Now, if we wanted to, we could find the composite center of gravity of this entire object, and it would, let's pretend that it would be right here, and I'll put a circle around it. It would move a little bit to the right because of the rod, probably not as much as I've shown though. So let's presume that we have a composite center of gravity right there. And you can go back to physics or statics where you learn to find the center of gravity of composite bodies. I'm not going to talk about that right now, but you could do that. Then you could move the center of gravity of the sphere to there, and move the center of gravity of the, move the moment of inertia of the sphere to there using a parallel axis theorem. And you could move the moment of inertia of the rod to there using parallel axis theorem. And then you would have a true IG of the system, and you would know where the center of gravity is, or CG. And then you could work with center of gravity kind of stuff. So that'd be one way to put this problem together, is bring the entire body together as one thing with a common center of gravity and a common moment of inertia. Instead, the author says, let's treat these as individual objects, but then let's add the equations together of the individual objects, and we're going to do it in one step. And by saying the sum of moments of all pieces about point O is the sum of all of the kinetic moments of all pieces about point O. Now let's look at what is going to cause true moments about point O. The mass of the sphere, the weight of the sphere through this large distance will cause a moment about point O. The weight of the rod through this 1 foot distance will cause a moment about point O. So we have the 30 kilogram, let's see, 30 pound, 30 kilogram, what was it? 30 pound. 30 pounds is the weight, and 3 is its moment arm about point O, and 10 pounds is the weight of the rod, and 1 foot is its moment arm about point O. And now we're going to have two different terms. We're going to have this term and this term. Okay, and each of those is the kinematic moment of a body about point O. This one would be the sphere, and this one would be the rod. And up earlier, the moment of inertia of the sphere about its own center of gravity was calculated. The moment of inertia of the rod about its own center of gravity was calculated. And so the kinematic moment of the sphere is IG alpha, and then this is the acceleration of the center of gravity of the sphere producing a moment about O. The acceleration of the center of gravity of the sphere, it's mass times acceleration of the center of gravity of the sphere times a moment arm of 3. But is that 3 alpha the acceleration of the center of gravity of the sphere? And the answer is it is. The thing is starting to rotate, okay, and so we'll have an alpha, and the tangential acceleration about an instant center over there would be a 3 alpha quantity, and the tangential acceleration of this rod would be a 1 alpha quantity. And why is there no normal direction acceleration? Because right now omega is 0. So, but let's back up a little bit. Using the equation sheet to get to this, we have on the equation sheet, I'm going to fold it so that we can see it. Sum of moments is equal to the I of a single body times the alpha of a single body plus the mass times acceleration of a single body being crossed with a radius vector from point P to the center of gravity of a single body. This is a single body equation. But what would we have if we wrote this equation for the sphere all by itself, we would have the moment of the sphere, 30 times 3, about 0.0. In this case, P refers to 0.0 in our picture. We would have this one term is equal to this term right here plus that term right there, and that would be a true equation. Then we'd write a second equation for referring to the rod and say the sum of moments of the rod, which is its mass times distance, a single term, is equal to an I alpha and a rho cross MA term. Here's the I alpha term for the rod, and here is the rho cross MA term for the rod. We would use this equation twice and have two equations. Is it then acceptable to take those two equations and add them together? Sure, and if we do, we produce this equation. So this is a true equation, and we might call it a system moment equation. The sum of all moments about a particular point in the system is the sum of the kinematic moments of each of the bodies in the system, okay, about that particular point. And each of the kinematic moments will be an IG alpha plus a rho cross MA. So that's the notation that the author likes to use. He likes to add them together. We could have written the individual equations if we had wanted to. I'll leave the rest of that example for you to study. And that finishes what I wanted to talk about in these videos.